Good morning and welcome to this morning's webinar on the evaluation of wear-corrosion synergy through Tribocorrosion studies. My name is Sarah Tishner. I'll be hosting the webinar for you this morning. Before we begin, I wanted to address a couple of logistical questions, housekeeping questions. All attendees are currently on mute. If you have questions, we do welcome those questions during the webinar presentation. You have a questions window where you're welcome to type in and submit questions throughout the presentation. At the end of the presentation, we will have time to take questions and answer as many as we can. For those we don't get to, we will answer offline with you via email or by phone. Also, at the end of the presentation, there is an exit survey. It's a very quick survey, maybe 5 questions total. We do appreciate you taking the time to complete the survey. That helps us to create and host more interesting webinars for you in the future. With that said, I'd like to introduce to you the presenter for today, Dr. Suresh Kuriri. He has a PhD in Metallurgical and Materials Engineering from the Indian Institute of Technology in Kharagpur. He has spent several years at the University of Central Florida as a postdoc researcher and is one of Bruker's senior research scientists with 6 patents to his name. He's conducted extensive research and development in nano, micro, macro tribology, nanomaterials, wear, corrosion, chemical mechanical polarization, and electrochemistry. He's been working with Bruker for the last 8 years, managing research and development and applications for the Tribology and Mechanical Testing Group. And with that, I'd like to turn it over to Dr. Suresh Kuriri.
Thank you, Sarah, for your nice introduction. And hello, everybody. Welcome to Evaluation of Wear-Corrosion Synergy through Tribocorrosion Studies, a webinar from Bruker. In this webinar, I will cover some of the topics which are listed on this particular slide. Tribocorrosion basics and applications, some of the basic of tribocorrosions, what it is, and how we work on tribocorrosion, and what are the things we get. And I will explain some of the applications. It has myriad of applications. I will go to next is electrochemical polarization methods. These are some of the techniques which are used for corrosion studies. And then I'll describe the module which is designed and manufactured by CETR, the Bruker-UMT group, and which is capable of doing tribocorrosion research and development and studies. I will also cover some of the standard tribocorrosion test procedures which are related to ASTM standards, American Society for Testing of Materials. Then I will discuss some of the results obtained through a CETR-UMT test system. And at the end, we'll have some time, about 10-15 minutes, for questions and answers. Let's start with tribocorrosion basics. You see on this slide, I put together the tribocorrosions. Tribocorrosion is basically consists of 2 well-established branches of science and engineering. Those branches are tribology. People are working for hundreds of years on tribology. And corrosion, which is again very well-established branch of science and engineering. Tribology deals with science of friction, wear, and lubrication. On the other hand, corrosion deals with materials degradation due to chemical and electrochemical reaction. When these two merge, tribocorrosion emerges. Tribocorrosion is a pretty recent field, maybe 5 to 10 years old, and people are working on this. This is an expanding area of research. And why tribocorrosion is so important? Because wherever there is a tribology and corrosion, they merge together, the material degradation is too much because of synergistic effect of these two phenomena. The tribology has mechanical component like sliding wear, abrasion, cavitation damage, fretting, tribooxidation, solid particle erosions, and so on. But today's webinar, I'll focus only on sliding wear type of tribocorrosion. Wear-corrosion synergy. You see on this particular view graph, we have a substrate covered with film, which is an oxide film, maybe some other types of film, which is a protective film. Say for instance, for example, stainless steel, and which has always an oxide film on top of it, which is a chromium oxide, which is impervasive. It doesn't allow diffusion of any reacting species. Thereby it protects the substrate. But what happens when there is a tribo, that is some kind of sliding wear is taking place on this particular film? That film immediately breaks. And when film breaks, the substrate is exposed to corrosive environment or chemicals, and this corrosion process an accelerated corrosion process starts, reducing the thickness of the substrate. When corrosion starts, it produces corrosion debris, corrosion products, wear corrosion products. They further enhance the wear process as a third body interactions, which acts as abrasive particles. So due to the presence of wear and corrosion, you can say the degradation of this material or substrate is too high. Initially, it has a thickness of, say, Xi0. At the end, thickness is reduced to Xi-T. So degradation of materials due to synergy of wear and corrosion is really high, huge. Tribocorrosion has myriad of application. As I initially said, it is applied almost all parts of engineering industries. I have just jotted down some of the major industries where tribocorrosion is involved, and study of tribocorrosion will be very important for this kind of organization. Say for instance, automotive industries where there are a lot of moving parts. Say for instance, look at any engine or any moving components which is working with the lubricated conditions. Lubricants might have chemicals, definitely always it has chemicals, additives, which interacts as corrosive, or there can be some corrosive agent from the atmosphere. They interact and tribocorrosion sets up. In some parts of engines, say for instance, where because of friction, there's a lot of heat generations, and due to this heat, parts might get oxidized, forming oxide films, which is called as tribooxidation. This can happen at a point when there is no lubricant present, or there is some kind of excursion of temperature due to some other regions, and this kind of tribooxidation can happen. So this is very important for automotive applications. It has applications in biomedical industries where when we deal with, say for instance, implants, say knee joints or hip replacements, parts which are moving or sliding or some kind of fitting conditions, they interact. There are wear debris, and these parts are exposed to corrosive environment, body fluids, and therefore there is a tribology and corrosions. These two aspects are involved, and tribocorrosion happens. Chemical mining and petrochemical industries, pumps, valves, propellers, heat exchange tubes, all these components are subject to tribocorrosions. Drill bits in mining or petrochemical industries, slurry transportation system where we are dealing with chemicals, aggressive chemicals, and abrasive particles in the form of slurry, tribocorrosion is present. Dental, very important. In dental, we use arch wire for orthodontic applications, or maybe some kind of implants, dental implants, where these implants are subject to attrition, subject to frictions with food particles, and also subject to corrosions from saliva. So tribocorrosion takes place there. In fact, this is a very concern. If you are using a nickel containing metal as archware for automotive application, this archware can leach, nickel can leach from this archware, and it can go into the body, which can be really harmful. They are trying to prevent this kind of leaching operations by coating these archwares with some kind of some organic coatings or coatings which will be inert to saliva. There are a lot of other applications in food industries, in marine, and lubricant research and development, where researchers are working on developing novel lubricants such as ionic lubricants. Tribocorrosion, I know only one case so far where tribocorrosions can be used as a beneficial process, which is in semiconductor industries, and the process is called CMP, chemical mechanical polarization, where use of mechanical wear and chemical interactions can be employed effectively to have good polarizations on silicon wafer. Tools for tribocorrosion study. As the name suggests, we need an instrument which can study the tribology, which is called tribometer, and electrochemistry, which is electrochemical measurement system. So tribocorrosion tool consists of two parts. One is tribometer, which provides controlled mechanical loading and relative motion, measures friction, force and normal force, and yields evolution of coefficient of frictions with time. It also gives materials removal rate. So usually tribometer will have some kind of system, either a profiler integrated into it, so that we can evaluate the wear extent of wear, that is wear volume. So we need to figure out the dimensions of the wear track, that is width, length, and depth. Electrochemical measurement systems actually performs electrochemistry testing. That is, it can measure open circuit potential. I'll explain all these terms later on. I have a few slides. Electrochemical polarizations, electrochemical impedance measurements, and this gives other information such as corrosion potential, corrosion current, from which rate of materials removal due to corrosions can be calculated. Tribocorrosion test requires specimens. For tribocorrosion test, it can be used for two ways. One is those who are manufacturing materials or researching on materials development, they can use their metallic material as tribocorrosion specimen. Or those who are working on chemical development, they can use a standard metallic material as a basic for comparison, and they can work on different kinds of chemicals, which will be their test specimen for tribocorrosion interaction studies. And typical results that we get after tribocorrosion studies are like, say, corrosion rate, effect of pH, scan rate. Scan rate is like how, that is also called sweeping rate, that is voltage sweeping rate, at what rate we are changing the voltage during polarization studies, electrolyte concentration, temperature, and behavior of metallic materials. And it can give synergistic effect of wear and corrosion. All these results can be obtained using tribocorrosion test. Here is a schematic of a tribocorrosion cell. It shows the tribocorrosion cell which has 3 electrode system. For any normal electrochemical system, you need to have 3 electrodes. One is working electrode, that is the actual metal specimen, and a reference electrode, which is basically an electrode used for measurement of potential of the metal, that is working electrode. A reference system can be a silver chloride, AgCl, or calomel electrode, or some other reference electrode. And there has to be another counter electrode, which is basically made of platinum, usually platinum. Sometimes graphite can be used, but platinum is the more convenient material, which is inert, which doesn't, and it actually conducts electricity. These 3 electrodes are connected to potentiostat, and potentiostat can have a programming module. In our systems, we have one software which interacts with our Tribology as well as our potentiostat or electrochemical system, where you can program how you want to sweep the voltage and measure currents, or you want to measure open circuit potential. All these things can be programmed. This Tribocorrosion cell will also have this wear experiment under electrochemical environment. So you have a ball or pin, and you can apply load, and this can move along these directions, which is maybe it is a sliding wear kind of stuff, and these working electrodes and all these other electrodes are immersed in the test solutions if the solution is to be tested in chemical environment. This system can also have a heating facility so that we can do biomedical tests, Tribocorrosion under biomedical conditions, where we can maintain this bath temperature, near body temperature, about 36 or 38 degrees Celsius. And there is a temperature sensor for that too, for controlling the temperature and maintaining. Now I will discuss a little bit about electrochemistry or electrochemical kinetics. Bear me 2 or 3 slides. These are like this is electrochemical kinetics on the surface of a working electrode, that is metal electrode. You know, when metal is exposed to any kind of electrochemical system, electrochemical solutions, it tends to form ion, and it goes into the solutions. We have seen it. If you take a copper and put into, say, hydrochloric acid or nitric acid, you will see that copper is continuously getting dissolved into it. And copper, that material becomes thinner and thinner. So metal is getting dissolved. But for this kind of dissolution to take place, it has an activation energy barrier for converting metal into ion and vice versa. So when metal gets converted into ion, it is called dissolution reactions, and which is written like this. M, which is metal, it loses some electron, Z number of electron, it forming an ion with G valency, G plus, and it gives a electrical current because of these electrons are moving under field. When the reverse reaction occurs, a metallic ion gets electron and it deposits as metal. This is called dissolution reaction or dissolution current, and metal deposition reactions gives deposition current. This is anodic and this is cathodic. Now this, in reality, these two reactions are taking place when under equilibrium conditions. These two metal dissolutions and metal deposition reactions are taking place simultaneously. And therefore, these two currents are actually equal, and you do not see any electrical current output. This current, that is one of them, metal dissolutions, anodic, or metal depositions, is called exchange current. When we calculate this in terms of unit area, it is exchange current density. And if we know exchange current density, we can calculate the corrosion rate. This exchange current density is a function of this activation energy barrier, exponential functions. K is a pre-exponential factor, delta G is the activation barrier energy, R is the universal gas constant, T is temperature. Delta G can be expressed based on number of electrons participating in these reactions, G, and farad, that is charge, which is moving under a potential, or we call it electrode potential. So if you multiply this, delta G can be equal, delta G can be expressed as minus GF into E in equation 4. In equilibrium condition, as I said, there is no net current flows. So dissolution current equals to deposition current. When we do polarization experiments to find out the actual corrosion rate, or I-core, we do polarizations, and this polarization is nothing but disturbing this equilibrium by applying external potential, either anodic or cathodic. Anodic means metal surface, we are making it more positive, and this shift in potential is called polarizations, which is denoted by eta, over potential. You can see there are three different kinds of polarizations can take place. One is activation polarizations, which is basically employing potential on the surface of the electrode, either anodic, that is positive, or cathodic, that's negative. Or there can be other two polarizations, which is called concentration polarizations, when there is a barrier for diffusion of reactive species from the bulk to the to near the surface of the working electrode, that is metal, and resistance polarization. I will just concentrate on activation polarization here, just to show you how this can be used to construct Tafel plot, where we will get corrosion current and at the end corrosion rate. Now you see on this picture on the right side, right top, the activated complex under polarizations, anodic polarizations. Metal surface is polarized by eta, so its barrier is decreased, barrier height is decreased. On the other hand, ion barrier height is increased by alpha Z, F is the Faraday, and eta, which is over potential. Now, when it is anodically polarized, you see the metal dissolution reactions is favored, whereas ion transforming into metal, that is metal deposition reaction, is less favored because this height, barrier height, is increasing. And we can calculate this barrier height for metal dissolution is decreased by a factor delta G star minus 1 minus alpha G F into eta, as shown here. And activation energy for metal deposition is increased by this amount. These new metal dissolution activation energy values can be used to calculate the dissolutions and deposition current in the next slide. Under anodic polarizations, metal dissolution current now is I equals to, again, that P exponential factor and exponential term containing the new free energy barrier, delta G star minus 1 minus alpha into Z into F into eta. If we simplify this, we get an expression for metal dissolution current, I0 exponential, and this. If we proceed similarly, we get an expression for deposition current, that is I deposition, as I0 exponential minus alpha Z F eta by RT. The net anodic current, which is flowing when it is anodically polarized, can be obtained from these two equations, 7 and 8, as I net, as this, which is expressed in equation 9. This equation is called Butler-Volmer equation. And this Butler-Volmer equation basically expresses net current flowing through the circuit with over potential eta. Now, this Butler-Volmer equation can be actually simplified, by approximation at high field conditions where your eta is really high, more than 0.1 volt. In that situation, this I net will be only dominated by the metal dissolution, and metal deposition reactions will be very minimal. And it can be, and in this condition, this polarization at anode can be approximated with the equations beta log I0 plus beta A log I anodic, where beta A is a constant known as Tafel constant, anodic Tafel constant. And on the other hand, when you do cathodic polarizations, applying negative voltage on the metal electrode, that is working electrode, this overpotential, cathodic overpotential, can be expressed with similar equations. These two combined called Tafel equations, which is expressed as eta equals to B log I0 plus minus beta log I, where I is the current, net current. This Tafel extrapolation is used to find out corrosion rate, I-core, which I will explain in the next slide. See, this is a polarization plot where you see it has two branches. This is the anodic polarizations, where overpotential is anodic, and cathodic branch, which is cathodic polarizations. And in the, if you approximate these linear portions of anodic and cathodic, they crisscross at a point which is actually I-core. Once you know the I-core, we can calculate the corrosion rate with these equations, where K1 is a constant, depends upon units used. I-core is the corrosion current, rho is the density of the metallic material, and EW is the equivalent weight. This is basically, this is derived from Faraday's law, second law. So we can have a corrosion rate of any metal from the Tafel extrapolation method. Now I will move to our Tribocorrosion tester. On the right, you can see here a picture of our CETR-UMT. We call it, that's the model number, CETR-UMT. And this is a universal materials tester, and Tribocorrosion module is one of the modules which is used for Tribocorrosion studies, where you apply wear, sliding wear, and electrochemical studies together simultaneously. It can go up to 20 Newton load. It has a programmable servo control. You can program fully how much load you want to apply, how you want to move it, how much distance, at what speed, or everything programmable. It can do ball or pin on plate type of weight test. Let me explain. Ball on plate is like you have a ball and you're applying load on this ball and on a metallic sample, and you're moving this ball over and over to do wear, sliding wear. In pin on plate, you have a pin instead of a ball. Here contact condition is different. You have a flat surface, pin, flat pin on a flat surface. But in ball, you have a ball on a flat surface. So contact conditions, pressures are different. Those pressures and other parameters can be calculated using Hertz equations. It has 3 electrode corrosion cell, potentiostat, galvanostat. Experiment can be done. We have a heating system which can go up to 70 degrees Celsius, which is pretty much sufficient for doing all kinds of experiments related to tribocorrosions. Corrosion resistance tribocorrosion cell, which allows one to use any type of chemicals, it is for this particular test. And we cover test as per ASTM standards. Here is a picture of this cell, and this cell, you see this is the cell. It is a this is connected to the potentiostat. All these connectors are there. This is a reference electrode. Then you have a counter electrode on the top, and metal specimen is sitting inside, which is shown on the right bottom corner. This is the metal specimen, and this whole thing is covered with chemicals. We have 2 different kind of design where you can have lot of chemicals at about 100 milliliter, which covers up to this level. There is inside, there is a mark level, or you can have very little amount of, like say maybe 5 milliliter, 5 to 10 milliliter of solutions can be used to study tribocorrosions. This is important because in some cases, some exotic solutions like ionic lubricants, you you will not have chance to have hundreds of milliliters of liquid for testing. You have very little amount of liquid during research, during researching. It's like costly and it takes time to produce in the lab. So our system can accommodate either high volume solutions or as little as 5 milliliters of solutions for Tribocorrosion studies. This cell is sitting on a drive, in this case a linear drive, which can reciprocate along these directions, and the whole thing actually can be put onto our UMT, Universal Material Tester. The data, this cell is controlled by the potentiostat, which is again programmable through computer. We have only one software, which everything is integrated into one software, one testing software, and that actually controls this potentiostat, Tribocorrosion cell, and the tribology apparatus for weight experiment. Evaluation of wear-corrosion synergy. This is, now I will explain how it can be done. This is primarily based on ASTM G119 standard. According to that standard, wear and corrosion, most of the time they form a synergistic couple. What does this mean? It means that when wear and corrosion present, the wear rate is increased, corrosion rate is also increased. Wear rate is increased because of the presence of corrosion, and corrosion rate increased because of the presence of wear. So actual material removal or material degradation rate, which is total T, is wear when there is no corrosion, that is pure mechanical wear, and pure electrochemical wear, plus a parameter, which is called synergy. This is more than the individual summation of wear and electrochemical corrosion. We need to find out the parameter, the synergy parameter is. To obtain that synergy parameter, we need to perform 4 experiments. First experiment is to find the corrosion rate, electrochemical corrosion rate in the absence of any wear, zero wear, corrosion with zero wear. This is done by doing simple polarization measurement, Tafel Extrapolation. You put a sample on that cell and just apply polarization, get a polarization graph, and from there you can calculate the CG. Then you need to perform another test, which is test 2, waste test in corrosive environment. No external potential or electrical current is applied. You put the solutions, put the sample, and perform a sliding weight test. And after the end of the test, you take out the metallic sample and evaluate the corrosion. Evaluate the wear track for its width, length, and depth, total wear volume, and find out the materials removal rate, total materials removal rate in the presence of wear and corrosive chemical. Then, test 3 is, here we need to find out the electrochemical corrosion rate in the presence of wear. So we do the similar experiment like test 2, that is electrochemical polarization when wear is present. So that sliding experiment is on. At the same time, we do electrochemical studies to find out electrochemical corrosion rate in the presence of wear, that is CW. And fourth test is repeat test 2, with a potential, means with a cathodic potential, applying around 1 volt of cathodic potential with respect to E core to obtain wear rate when there is no corrosion. In fourth test, actually, we are suppressing corrosion by applying cathodic polarizations, very high cathodic polarizations. And we want to find out wear rate in the absence of corrosion. Once we have these 4 parameters, C0, T, CW, and W0, we can calculate the synergy by considering that T equals to W0 plus C0 plus S, where S is actually 2 parts. It has two parts. One is change of corrosion rate in the presence of wear, and change in wear rate in the presence of corrosion. And these two terms can be calculated from the known CWC0, total materials removal rate, and W0 and CW by this formula, equation 16 and 17. Now, total synergism factor as per STMG 119 is T by T minus S. S is already known from this equation 15. And corrosion augmentation factor, which is basically enhancement of corrosion in the presence of wear, is CW by C0. On the other hand, wear augmentation factor is W0 plus delta WC divided by W0, as shown in equation 19 and 20. This is an example of electrochemical corrosion rate evaluation experiment, polarizations done on cast iron at 0.1% sodium chloride solution. And you see there are three experiments which are actually very repeatable. We get in the form of I core, corrosion current, of course E core also in available, and from this we calculate corrosion rate. This is this is showing a wear scar profile after Tribocorrosion experiment is done. You see there is a wear scar, and you can evaluate this wear scar by any profiler. We have integrated profiler with our system, and that profiler can be used for measurement of this wear scar volume, that is width, depth, and length known. From there you can calculate how much material is removed. From that we can have the wear rate. This particular wear scar measurement is done for test 2 and 4 out of this 4 tests to find T, total corrosion rate, total materials removal rate, and wear rate in the absence of corrosion. And so corrosion is substrated by applying cathodic potential of 1 volt with respect to the E core. Once you have those data, you can calculate those numbers. Say for instance, here is an example for 316 stainless steel in 0.9% sodium chloride solutions using 5 Newton load at certain speed, 0.4 millimeter per second. This experiment was conducted with an aluminum ball, and we have all this calculation like total synergism factor is about 6, corrosion augmentation is about 1.8, and wear augmentation factor is about 6. Tribocorrosion setup can be also used for measuring open circuit potential, which is basically in that electrochemical cell when you disconnect the counter electrode, the platinum electrode, and measure potential on the electrode surface with respect to the reference electrode. You don't apply any electrical current or voltage on the specimen, that is metal specimen. This can be actually OCP measurements is very important tool to understand what is happening on the electrode surface during tribocorrosion. Here is an example. This experiment was done on again 316 stainless steel in sodium chloride solution. You see, when we do not apply any force, mechanical wear is absent, but same setup, no movement or no application of force. You see this is the blue line is actually a potential, OCP. It has a rising tendency, which means that it is forming some kind of oxide surface on top of it. This might be because of oxygen present in the water, that solution. It is not deaerated, and it is forming an oxide surface, precipitating surface, which gives protection. But as soon as we apply the Tribo, that is mechanical wear, it started sliding with the load of 5 Newton. You see this film is trying to break, and it broke after some time. You see this friction force increased a lot. This is the friction force, and friction force it is like a sawtooth curve. It has a positive and negative because of directionality. So it is going forward and backward. That's why there is a positive and negative number in this friction force. Friction force changes. At the end, this film is totally broken, you can see. But interesting is when you remove the load and stop the movement at this point, you see it started forming the film again. So this type of experiment, OCP measurements during Tribocorrosion studies, is very good indicator to know how this film is working or not working to prevent protection, to prevent corrosion of or materials degradation during actual application. This test can be done on any metallic sample, or it can also be used to study the effect of lubricant or effect of chemicals on any metallic sample during Tribocorrosion. I have almost come to the end, and I conclude by saying that Tribocorrosion test procedure is an important method to evaluate metallic materials or solution for their performance under simultaneous wear and corrosion conditions. CETR-UMT test system can evaluate wear corrosion synergy of an electrochemical system involving chemicals and metallic materials, including coatings. Now we are open for questions and answer session. Sarah, do you have questions?
Sure. Terrific. Thank you for the presentation, Suresh. Folks, I invite you to type in questions into the question box in the webinar software and submit them. We'll take questions now. There are a couple of questions here. Let me just gather them together. We have a question here. Early in your presentation, you mentioned that the tribometer can measure wear volumes. How is that measured, and can you differentiate between mechanical and tribocorrosion dictated wear volumes? So maybe we'll take it as two questions. One is you mentioned that there was the tribometer can measure wear volume. So how is that measured?
Okay, to answer the first part of this question is that tribometer is equipped with G encoders, which actually measures the position of the ball tip. So when there is a material removal and there is a wear taking place, you can track the G movement and you know the depth. We can calculate the depth. We precisely know the length of the wear scar because we fixed it during the experiment. We just decide how much you want to go, 4 millimeter, 2 millimeter, or 1 millimeter, whatever. And you can, from that, you can have some kind of idea, but it is not accurate. So what you have to do is, once you finish the experiment, you start using the integrated profiler, which can profile the surface and measure the volume.
Okay, following on from that, can you differentiate between mechanical and tribocorrosion dictated wear volumes?
Yes, you can differentiate because, as I explained in the presentation, that you need to do several experiments to differentiate those. You need to, say for instance, you just perform a test with tribo on and chemical is on, you get the total wear volume, that's a T, and then you perform 3 more tests. One is with suppression of corrosion media by applying cathodic potential around 1 volt with respect to the E-core, and then you find one parameter which is CW in this case, and you can do other 2 experiments. All these 4 experiments are needed to differentiate between wear due to only mechanical or wear due to mechanical plus chemical.
Terrific. There are a couple of more questions that have come from this initial one. The first, what is the area used for calculating the corrosion rate?
Okay, good question. Now, area is used basically the exposed area of the sample. I have shown you how this sample is mounted. You have a circular area which is used for measuring the electrochemical corrosion rate because everything is exposed to the chemical. Now, when you do the tribocorrosions, you need to measure only the wear track, area of the wear track.
Okay. Using an aluminum ball, you mentioned, for measuring the corrosive rate, but why not some other metal? Would maybe a higher hardness factor? Is there a reason for the type of...
Oh, okay. No, this counter body for this Tribo experiment has to be non-conductor of electrical current. Otherwise, it will interfere with the measurements. That's why it has to have ceramic, number one. Number two is that it has to have hard material, and alumina is hard, or sapphire, some other material which is hard, so that that ball itself will not undergo any material removal. And the sample, which is metallic, that will undergo wear.
Okay. Can you speak to how much chemical solution is required for the Tribocorrosion test?
As I explained, chemicals required is, we have two different kinds of design. First one where you can use maybe around 100 milliliter of solutions, and the other one where you use only very small, that is about 5 milliliter of solution.
Okay, give me a second here. I'm just trying to pull together some other questions. And then I guess you spoke, there's a question here regarding the reference electrode. So you spoke a bit about the pin for measuring the corrosion rate, but what about precautions to take preventing contamination in general?
Actually, I didn't cover this in the presentations I would have, but I'll explain it now. I'm sorry. This reference electrode is very important. It has to be preserved. Its tip has to be preserved. It should not get contaminated. Otherwise, you'll get all kinds of wrong measurements, potential measurements, and the whole experiment might go wrong. You'll get wrong data. It is done. This reference electrode tip is preserved by using some kind of Lugin capillary. A capillary which is attached to the tip of the electrode, and it is filled with same kind of solutions which is used to make this particular reference electrode. Say for instance, for AgCl we use potassium chloride. So that Lugin capillary has to be filled with potassium chloride solution, and the whole thing is actually installed in the Tribocorrosion cell, so that that particular capillary will prevent the contamination of the tip of the reference electrode. When you are not using this reference electrode, as usual, you need to take it out, remove the Lugin capillary, rinse it with double distilled water, and preserve this particular reference electrode into a preserving solutions. It also, again, it depends on what type of electrode you are using. If it is AgCl, put it into 1 molar potassium chloride solution for preserving. You can preserve for months, no problem. It will not change. Again, if there is any doubt, you can have a set of reference electrodes which are not being used for measurements or doing experiment, and you can compare the standard potential with other reference electrodes, just to make sure that your reference electrode which are in use is in good shape.
Terrific. From there we have a question regarding temperature limits for the testing. So most engines, it's in reference to engines running at about 200 degrees C, and is there a way to simulate that on the CETR-UMT?
At present we do not have that, but that is related to tribo oxidation, and I put that in context so that is another aspect of tribo corrosion, which is dry corrosion, where what happens is because of temperature rise, there is an oxidation, surface oxidation of metal. Say for instance, valve which is sitting on the engine head, and it is exposed to a temperature, say 200 degrees Celsius, maybe 300 in some cases, and it is at the same time it is rubbing against the cylinder head, engine head, where valve sitting or say some other things, where there is oxidation taking place, as well as there is a aggressive environment of gas like oxides, carbon dioxide, carbon monoxide, so many other things inside which reacts. But at present we do not have this. We cannot really simulate high temperature for Tribocorrosion measurements in our system, but this is a limited case. It is a special case, and most of the Tribocorrosions which are in questions are basically related to aqueous environment, meaning that they require some kind of water-based solutions where temperature doesn't go more than probably 80 degrees Celsius.
Okay, there are a couple more questions here. Getting back to the discussion of, or the question regarding the area that's used to calculate the corrosion rate, there is a question or a comment asking to essentially, I guess, clarify the film-covered area versus the wear scar area and how they might corrode differently. So can you speak to that? That in particular, the variation in corrosion rate, I guess, over the whole area versus specifically where the wear scar is?
Okay. Let me explain this again. This is when we are doing, out of these 4 experiments, in one of the experiments we are dealing with where the whole surface of the sample is exposed to the chemicals, and probably electrochemical reaction is taking place on the entire area, whereas Tribo is only on the area where this ball or pin is in contact. Now this particular, and one case where you want to see that you want to measure only the material degradation due to the wear area, and in the, say for instance in case of CW measurements where you want to apply a cathodic potential 1 volt with respect to E core, and you want to find out the wear rate. In that experiment there is no much error because there is no corrosion taking place away from the area where this ball is engaging. So that is fine. CW measurement is absolutely perfect. T measurement is also perfect because we assume that corrosion is much less than, materials removal rate due to corrosion is much less than the mechanical wear. And there will be error, maybe 2 or 3% or 5%, but it should be okay. But for measurement with measurement of wear with corrosion with wear, when wear is involved and you do electrochemical polarization study to measure CW, then there might be interactions of the area where corrosion is taking place and where corrosion is taking place, but there is no tribology like mechanical wear taking place because of asymmetrical area. In that case, you prefer to prevent it somehow, either by some kind of coating, unreactive coating on the surface, or we have a different methodology not using ball or pin, but you can use a cylindrical surface where entire surface will be covered for mechanical wear, and it will not add any error.
Okay. We have, I think, maybe time for one more question, and then also just let me just answer really quick. There's a question about the presentation. So you'll all receive an email regarding the presentation slides and the recording of the presentation. They'll be available for download later this week. You should receive an an email with the links to our website where you can pull this, download the presentation slides as well as listen to the presentation again. So one last question that I have here, it says for the passivating metal and alloy, the anodic Tafel polarization curve may be influenced by an applied load. So what load is optimal?
I'm sorry, Sarah, could you please repeat this, the last one?
Sure. For the passivating metal alloy, the anodic Tafel polarization curve, I don't know if I'm pronouncing that right,
it's correct.
may be influenced by an applied load. So what load is optimal for that?
That is actually, it can be this applied load basically may not change too much, but stress, load divided by area, that is more important. But that has to be studied for each individual system, how it is really affecting the actual measurements. That has to be studied individually. At this point, I do not have a really elaborate answer for this question.
Okay. One more has snuck in here under the bell. Really quick, what happens in the final graph in the last 300 seconds when you remove the charge after the test? The OCP is lower in height in respect to you in what you obtained at the beginning before applying the charge.
Yes. Okay. At the end, when I actually remove the load, then you can see originally the OCP was at the bottom and it started going up once you remove the tribo part. It means that once you remove this mechanical weight, this film formation is taking place and it is trying to follow the initial path. It is going up. It is showing a rising trend, potentially showing a rising trend. And eventually it will try to passivate the metal because of film formation. So this shows that tribo has actually an effect. Whenever there is a tribo, OCP is going down, means more metal dissolutions. But when you remove the mechanical weight, it comes back to passivation. But it takes time because there are several things going on there. There may be not uniform surface because of interactions with the ball and the metal. There may be some rugged surface area change. There are so many weight debris which are also affecting the effective formation of the oxide film on the top.
Okay, and with that, I believe we have used up our hour. There are a couple of other questions that we didn't get to address, but rest assured we will contact you via email, answer your questions, and I'll hand it over to you, Suresh, for final words.
Thank you, Sarah. Thank you for helping me on this question answer sessions and organizing this session. Thank you all our viewers and listeners for joining us today morning, making time to join us and to listen to our presentations and our product information and other details. Thank you so much. Bye-bye.
Bye-bye.